Hello. Actually, after this week, I don't know what my talk is about anymore, but I just gonna flash a few slides with you, hopefully triggering some of the discussion. I want to show you some of the latest work that we did, and hopefully can add to the discussion. So there were lots of discussions on presentations of Borg already and field level inference, so I'm not going to do that. Just a very quick overview. The Borg is basically a field level inference machinery that's based on Hamiltonian Monte Carlo. The aim is to reconstruct the 3D initial conditions and optionally also cosmological inference. It's building up on a differentiable cosmological structure formation model like COLA or something else. And we have explicit likelihood models in there, various different explorations. That's it. We can, in this pipeline through forward modeling, also handle all kinds of survey geometry and systematics. And Natalia has shown some of that, and Eleni has referred to that as well already. So coming back to the discussion on what we call field level inference, we can maybe even ask the more general question what we want to achieve in cosmology. And in a Bayesian framework, that's basically all the questions we can write down, right? In Bayesian frameworks, your question mark goes to the left of the conditioning bar, and everything you know goes to the right of the conditioning bar. So we want to know what is the initial conditions of the universe, X, the corresponding cosmological models, parameters, omega, and then what's ultimately the actual model. And you can see that we can factorize it according to the product rule. And the nice thing is that you can, by just doing that at that level, basically read off what these individual terms actually mean. We have the model evidence here that's basically asking the question, what's the world model? Is GR or something else? We have parameter estimation that's then, once we have specified the model, what are the corresponding parameters in there. And both of these two first terms in this factorization, they describe the ensemble behavior of our universe, right? So they behave the average behavior of our universe, but not the specific one. And the last term here right now, that's basically the term that describes the specific universe we are looking, it describes our universe. And that is information on the particular initial conditions, but also cosmological environment. It encodes everything that's not encoded in the averaging, that is orientation, alignment, and location. That's basically in there. And it's actually interesting to, if you read documents on or papers on the current anomalies in cosmology, then you can easily see that you can assign them to these different things, right? So we have anomalies with respect to the parameters, H0, but we also have anomalies with respect to these particular things like large bulk flows and, I don't know, globally aligned galaxy spins and so whatever. So you can nicely see that you can basically decompose cosmological questions in a very well formulated and actually not problematic way that does not allow for so many differences of interpretation. So in particular, what we want to call field level inference is basically given by that. It's the joint distribution of initial conditions and omega given the data and the specified model. So I think that's the definition of what we call field level inference, and that's the cleanest definition here. Just referring to some of the things that we have been done within the Borg group and within Aquila. Natalia has been doing this, but other people have been exploring the joint inference of initial conditions and cosmological parameters, like Adam Andrews working on primordial non-Gaussianity, and Natalia Porcaris and others. But the general answer is that it allows us to give a little bit more, actually significantly more cosmological constraints in this particular framework if we can handle this. So these studies have all been done on self-consistent tests and at fairly coarse resolutions, but they look already very, very promising. In particular with Adam, we see that there is a scaling relation, that increasing resolution will help. But there, of course, then comes for the curse of also having to model everything. So in this particular presentation, I want to focus on this last bit here right now a little bit, so getting the initial conditions right, and in particular, as a demonstration, that's a project we have been working on recently because we think that's actually the hardest part for that before going to a cosmological parameter inference with real data, to see if we can control that at a significant level in actual observations. And I just want to show you a project done by Stuart McAlpine on the 2M++ survey. That's roughly 70,000 galaxies around us. And the reason why we are looking into the nearby universe, not at cosmological volumes, is first of all, the nearby universe is an excellent physics laboratory. We have excellent complementary data that we do not have at larger volumes. And it's exquisite for field level inference because it's cosmic variance dominated. It's a prime target where we cannot work with ensemble statistics, where we actually need to work out specific realizations. So that's why we consider nearby universe as a target for exploring how well we can do. So the work by Stuart aimed at applying the Borg algorithm to this kind of data set, and the outcome of that is a posterior distribution, as we have heard here quite a lot. So the posterior distribution is here represented through an ensemble of Markov-Chain Monte Carlo samples, which when averaged over will give you the ensemble mean. So one of the things that's aligned with some of the discussions we had is model misspecification. So one of the things that we figured out over the recent years, is that if your inference model does not have sufficient fidelity, you will still get good initial conditions that can even align with the ground truth and so on. But at the very moment you take these and forward that in a high fidelity simulator, and then ask the question, is that actually reproducing the large case structure to a significant degree? And you figure out not necessarily. And that could just be that the gravity solver that you use for inference doesn't have the full time resolution, and that's problematic in high density regions and so on. So what we typically do from now on is we put our inference models through a simulator. In our particular case, we use Swift. And then we use a full n-body simulator to basically have a proper modeling of all that. And you get a posterior predictive distribution of the cosmic large-scale structure than this. And the requirement is that that should match. So just to give you an idea how this looks like, this is our digital twin of the nearby universe, one of these realizations. We blend in white the actual galaxies of the nearby universe, and you see that it's a nice visual match. But visual match is not necessarily compelling. So let's have a look if we can make a statement on how physically plausible that is, or is there any glitches. And these are the typical statistical summaries that everyone would look at: cosmological power spectrum, reduced bispectrum, and actually the little troublemaker is always the halo mass function to get that right, in particular at the high mass end, because there is where glitches appear. And the nice thing is that we get a consistent match with random simulations, so there's no obvious glitch with these things. And I don't know, if you look in the literature, there's lots of discussions about that getting the halo mass function at high mass end is very problematic. So that's actually what we worked on quite a lot. So independently, I think people who actually work on that with real data know that getting these results to that accuracy is non-trivial, because your likelihood overrules all your priors, right? Your priors are actually very weak. We have a few million pixels in there. They screw it all over. So that is a non-trivial result, even though that's what should be expected. So let me ask you a question. So if you get that, how good is the representation of the actual universe, right? All that's matching, you have no idea if that's representative of the actual universe. Nothing of that tells you it's a match for the universe. It tells you it's not completely off, but it tells you that it's not related to our universe. The particular problem that we have, and the question is how we can handle that, And one of the angles through that is that we basically took prominent structures surrounding us to see if we reproduce them actually. And just to show you, I mean, look at the halo mass function. It's a huge dynamic range that we have to cover. And let me start that again. So basically, these are posterior predictions for the for selected 4 massive halos surrounding us. So just to show the degree of detail that you can basically recover, and you get the full posterior over them. So all of these are different variations for these major clusters surrounding us, all compatible with the data to a degree that is very high fidelity. So we looked into many details of these things, and all these studies are not necessarily fully converged or completed. So we're looking in lots of metrics to see if posterior predictive tests pass, like cross-correlations with TSZ, X-ray, and so on. All of that looks very interesting and promising. But the major problem is that for field-level inference, there doesn't really exist a baseline comparison in literature. Yes, everything is cosmological statistical summaries, but that's not sufficient for field-level inference. One of the things that we basically want to do is use that for cross-correlation. So that means we need to have a high spatial accuracy. And Carolina showed that it's very challenging to get the positions of clusters right. So they were jumping between different pixels. So one of the first things you could check is your positioning okay with respect of your clusters that you identify in your digital twin? If they align with the actual positions of the objects that you get in real data. These are the red dots from our posterior simulations. And you see that we typically have a 1 degree accuracy on the sky. And in green, I show you the pixel width, right? So using the physics model, actually, we get on average an accuracy that's higher than the constraint of the pixel. So we get sub-pixel accuracy by doing that. So that is non-trivial. We have seen that before, that is a significant challenge in doing that. Other thing is, can we basically also recover masses of these objects, positions and masses? So here's the mass of the coma cluster. The green histogram is our posterior over the sample. And I just want to show you the current literature status. So these white dots, I apologize for that, but these is basically data in the literature. And they have been taken from different probes like dynamics, X-ray, TSZ lensing, and you see they scatter broadly. They exclude each other. That's the observational status we have about clusters that are actually in our backyard. So we have a nicely peaked distribution, and we can do this for all the clusters. We get the similar results, and we can compare with the literature, and you see that. And that's not insignificant because of the steepness of the mass functions. We may not have too many massive clusters in the nearby universe that would rule out lambda CDM. So let me move further. We also don't know how good we are with respect to others. And in 2023, Pfeiffer et al., they put out something which they call the local universe model, because this is from the CLUES collaborations. They do constrained simulations, and they would like to know what kind of simulations they should pick as a good representation for the actual universe. So all these metrics are not super, but they are the existing things that we can use to compare in literature. And part of the community needs to develop better metrics. But the idea here is very simple. So you have your observed halo in yellow, and then from your posterior simulations, you will have counterparts in your digital twin that's surrounding it. And you just ask the question, how likely is it that a halo within the vicinity of my observed object has been or is not there by chance in a random simulation? So the null hypothesis is it is just a random chance alignment. And you then ask if conditioned on the mass of the object and the distance of the object, can we reject the null hypothesis that is just a random point? So that's basically there. Again, this is not the best metric, but it's a certain point of covering. So it's a detection rate for these, and these are our results. So we average have a very, very high detection rate. We are actually saturating that metric quite easily. And when we look in comparison to the state of the art by Pfeiffer et al., you see that they have 20 to 30%, and we have almost 100% detection rate for all the objects that we could actually compare between those things. So we are way beyond state of the art. It's also important that these are only tests for each individual object, but not jointly. It's not asking if you jointly get them all correct. And that's a much, much stricter. We get them jointly correct. So that's a much, much tighter because of the concentration of measure in the product. It's a much, much tighter constraint. Again, this is the only metrics we have for comparison. Because of that, Richard Stiskalek actually was interested in asking the question, how well is actually the model for the dynamics that we have, because we actually get velocity fields as well. So the question is, how good are these velocity field constraints with respect to the state of the art in the literature? And he basically decided to do this in a Bayesian model comparison by basically calculating the evidence. So we take as a model the different velocity field reconstructions, and we compare them to different methods in the literature, which are listed basically here. The Carrick et al. 2015 is a standard in the community that's used for H0 and supernova analyses. And we also use reference data sets that we did not use for our inferences. So these are posterior predictive tests. So these are the different data sets. So we use a model comparison. So we take the delta log. So that's basically a base factor, the log 10 of the base factor. And we measure basically performance compared to the state of the art in the field. So 0 means that you're exactly as good as the Carrick et al. Negative means you're worse, and positive means you're better. And you can basically see that the Stopira 24, that's one of the previous Manticore or previous Borg reconstruction of the local universe. And we have the Manticore is basically on all these different data sets, outperforming all other reconstructions. We are even outperforming them on data sets which they used for their inferences. So this is pretty tough. Okay, I will be quicker right now. So that's basically my summary about this. So we have a high fidelity digital twin that's by all means that we can test right now best in class. If you're interested in following this project, have a look at cosmictwin.org, and we put some data. And Guillaume just asked me also to be a little bit provocative, because we also did a little exploration in basically looking at the local group. So roughly 40 megaparsecs surrounding us, taking velocity data of, I think, 40 galaxies surrounding us. And then we are developing a Borg version which has a zoom-in reconstruction. It's basically a 2-grid version where we have a coarser grid roughly covering 40 megaparsecs and then zooming in onto the local group. And then doing a posterior inference with that, and that's work by Ewout Wempe. And what you can see here is these 5 posterior formation histories of the Milky Way Andromeda pair in the local group. So it's a proof of concept, but it's basically a demonstration that you can do these things with actual data. And you can see a few things there that needs to be investigated. For instance, they always typically form along a plane. You can measure masses of galaxies, but you can also make tests, posterior predictive tests on the rotation curves of Milky Way and Andromeda and compare that to literature, and that's what you can see here. All that's very preliminary, and it's just a proof of concept, but it's interesting to see that with this kind of field level inference, you can open up new things. So I'll just leave that here. Thanks a lot.
Thank you very much, Jens.